All right, exams are coming up, so let's do a super quick, high impact review on the fundamentals of electronics. We're talking about the absolute bedrock physics, the stuff that makes everything from a simple diode to a complex transistor actually tick. Let's jump right in.
Seriously, just look around you right now. That phone in your hand, the laptop you're on, the screen you're watching this on. What's the one thing, the one fundamental principle that makes it all possible? It's kind of amazing when you think about it, but it all boils down to how one tiny, tiny particle behaves. And that particle, of course, is the electron.
So here's the roadmap for this review. We're going to start super small, inside the atom itself. Then we'll zoom in on the most important players, the valence electrons. You'll see how they're the key to sorting materials into different types. After that, we'll look at a classic matchup, silicon versus copper, to make it all real. And we'll finish up with the big one, the ultimate rulebook for all of this, energy bands. Let's do it. All right, first up, if you really want to get what conductivity is all about, you can't start at the circuit level. Nope. You have to go way, way smaller. We're talking about getting down to the atomic level, the fundamental building blocks of, well, everything. So let's picture the atom using the classic Bohr model. It's really easy to visualize. It's basically a mini solar system. You've got the nucleus in the middle, kind of like the sun, packed with positive protons and neutral neutrons. And whizzing around that nucleus are the electrons, just like planets. It seems simple, right? But the secret sauce for all of electronics, it's hidden in those orbits. Okay, so these orbits aren't just all over the place. They're actually very organized, grouped into these specific energy levels that we call shells. And here's the key rule to remember. The further an electron is from that central nucleus, the more energy it has. Think of it like floors in a building. The higher up you go, the more potential energy you have. Same idea. Okay, so we've got the basic atomic layout. But here's the thing. When it comes to electricity and how things conduct, not all electrons are born equal. Some are way more important than others. In fact, we need to focus on the absolute VIPs, the rock stars of the atom, the valence electrons. So what is a valence electron? Super simple. It's an electron in the outermost shell of an atom. That last, most distant shell, we call that the valence shell. These are the electrons on the very edge, the ones that get to interact with other atoms. They're the ones making all the deals. And that's why they're so unbelievably important, because they're on the outside, they're the ones responsible for chemical bonding. But for us, for electronics, they literally determine everything about a material's electrical properties. Is it going to be a conductor, an insulator, something else? It all comes back to how those valence electrons behave, period. Which brings us to probably the single most important number you need to remember for this topic. And that number is 8. An atom is at its most stable, its most content, let's say, when its valence shell is perfectly full with 8 electrons. This is the rule of 8, and it is the key that unlocks why different materials act the way they do. So now that we know about this magic number 8, we can actually start sorting materials. All materials. It just depends on two things: how many valence electrons they have, and what they're willing to do to get to that stable number 8. This lets us put everything neatly into one of 3 buckets. And here's the golden rule of conductivity, right here. The further away an atom is from having a full shell of 8, the more conductive it's going to be. Why? Because if you only have 1 or 2 electrons out there, it's way easier to just give them up and drop down to the next stable shell. And that's what conductivity is, the freedom of electrons to move. This chart makes it super clear. Look at conductors. They've got only 1 to 3 valence electrons. They're dying to get rid of them. It's so much easier than trying to find 5 or more to complete the shell. So they lose them easily. Now flip over to insulators. They're sitting there with 5 to 8. They're so close to being full and stable, they will hold on to their electrons for dear life, or even try to steal one from a neighbor. And then you have the weird one in the middle, semiconductors. Exactly 4. Perfectly balanced. They're not desperate to lose or gain. And that special in-between state is what makes them so interesting. All right, theory is great, but let's make this tangible. Let's do a little case study, a head-to-head battle between 2 titans. In this corner, a classic conductor, copper. And in the other corner, the king of modern electronics, silicon. Seeing them side by side will make this all click. Okay, so here they are, the atomic models for copper and silicon. Don't worry about all the inner shells for now. Just look at that very last ring, that outermost orbit. That's the valence shell. And the number of little dots you see there, that's the whole story. So let's break this down. Take a look at copper. See that? Just one single electron out there in its valence shell. It's barely hanging on. That makes it incredibly easy for that electron to break free, which is why copper is such an amazing conductor. Now look at silicon. It's got 4 valence electrons. Its shell is exactly how full. It's not really motivated one way or the other. It doesn't want to give them up, but it doesn't desperately need more either. And that's what defines a semiconductor.
So, we've established that valence electrons are the key, but for the exam, you need to know the deeper physics of why. Why does having one electron make something a conductor? To answer that, we have to talk about our final and most important concept, energy bands and energy gaps. Remember how we said electrons live in different energy shells? Well, when you have a whole bunch of atoms together in a material, those shells merge into these wide energy bands. The valence electrons all live together in what we call the valence band. Now, for an electron to do any work, to conduct current, it has to jump up to a higher energy band, called the conduction band. And the space between them? That's the all-important energy gap. You can think of it as a hurdle. It's the amount of energy an electron needs to overcome to be free. So let's start with an insulator. Just look at that energy gap. It's massive. It's like trying to jump across a giant canyon. An electron in the valence band would need a huge jolt of energy to make that leap. Under normal circumstances, it's just not going to happen. So the electrons stay put. No free electrons, no current. Okay, now for the semiconductor. See the difference? The gap is so much smaller. It's more like a small ditch than a canyon. Now, electrons can't just wander across on their own, so it's not a great conductor. But if we give them a little push, a little bit of energy, maybe from heat or light, they absolutely can make that jump to the conduction band. And that ability to control when they jump, well, that's the whole secret of electronics. And last but not least, the conductor. And this is the easiest one of all. What gap? There is no gap. The valence band and the conduction band are actually overlapping. It's like they've merged into one big superhighway. The electrons are already in the conduction band, ready to go. They are totally free, which is why it takes virtually no effort to get a current flowing. All right, let's nail this down for the exam. Here are your key takeaways. 1. A material's conductivity all comes down to its valence electrons. 2. The magic number for a stable, happy atom is 8 electrons in that outer shell. 3. Conductors with 1 to 3 valence electrons have overlapping energy bands, no gap. 4. Insulators with 5 to 8 have a huge energy gap. And 5. Semiconductors with exactly 4 have a small, manageable energy gap. Get those 5 points down cold and you're in great shape. So let's end with a question to chew on. We've just shown that semiconductors are kind of meh. They're not great conductors, but they're not great insulators either. They're stuck in the middle. So how in the world did this just okay material become the absolute cornerstone of every single piece of modern technology? The answer, as we hinted, is in that small, controllable energy gap. It's about our ability to turn that mediocrity into pure magic.